Hello, my name is Diane Nguyen, and today I will be discussing a novel security technique described in the following paper, Application-Level Autonomic Hardware to Predict and Preempt Software Attacks on Industrial Control Systems. I'd like to acknowledge the authors of this paper, Lee Lerner, Zane Franklin, William Bowman, and Cameron Patterson, all from the Bradley Department of Electrical and Computer Engineering at Virginia Tech. This paper was originally presented at the 2014 44th Annual IEEE IFIP International Conference on Dependable Systems and Networks. So just as a quick overview for the rest of the presentation, I'll be going over the background, motivation, current approaches to ICS security, and the novel security approach presented in this paper. In terms of background, when it comes to industrial control systems, there is a potential for large-scale disruption and destruction caused by malicious reprogramming of process control systems. Most industrial control system attacks focus on the exploits of network protocol and supervisory platforms to modify commands given to PLCs. The motivation for this paper is that most security measures involving industrial control systems are reactive rather than proactive, and they also, don't operate in real time. This means that malicious software can still perform some damage to a system before security measures are applied in order to restabilize it. Current approaches to industrial control system security can be categorized into general security methods and industrial control system specific methods. The general security methods include zones of trust, which delegate permissions for privileged operations at different layers or zones in both software and hardware. These zones of trust can also be integrated with system architecture extensions. An example of a system architecture extension is Trust Zone, which is an ARM extension that allows certain applications to run in a secure zone running under a distinct kernel in a separate memory space and can access certain hardware resources that are unavailable to applications that run in the normal zone. The novel technique proposed in this paper utilizes TECEP, which stands for Trust Enhancement of Critical Embedded Processes. It's a design process that includes malware mitigation in the control system development process. Additions were made to the TECEP design flow in the context of industrial control systems, leading to the design of a system-on-chip platform for ICS malware mitigation. So the objective of industrial control system malware is actually PLC behavior modification from process harming MTU commands or updates to control, kernel, and driver code. Recent industrial control system specific protection mechanisms include replicating SCADA network gateways and MTUs, and also runtime monitoring software. But these methods are still reactive in nature. The problem with reactive methods is that the control system is already compromised, so corrective action must be taken to restore the system. The method presented in this paper, which is application-level autonomic hardware, is a much more proactive approach. It is an active defense that cannot be disabled by any MTU command or PLC software update. It utilizes FPGAs to create a system-on-chip security platform. It's transparent to the control system designer, and it can anticipate controller behavior and system state for a short period into the future. To explain some of the terminology used to describe the proposed solution, both hard and soft processors were used. A hard processor is a physically implemented processor on the FPGA board. It's preferred when it comes to balancing performance and cost, and it's also not limited by the speed of the FPGA fabric. A soft processor, on the other hand, is a processor implemented within the FPGA fabric. It's also more flexible in terms of modifications, but on the other hand, it's limited by the speed of the FPGA fabric. The hardware design discussed in this paper can both monitor and possibly override software operations in real time at the lowest level, so at the I/O pin level, of a system-on-chip platform containing a microcontroller with configurable logic. By synthesizing the solution into hardware, it can also resist software reconfiguration attacks. The new protection scheme proposed in this paper leverages TECEP, which, as a reminder, stands for Trust Enhancement of Critical Embedded Processes. This integrates malware resilience into the control system development process. TECEP helps ensure process stability that doesn't rely on trust in any software layer on an industrial control system node. It helps achieve isolation and predict future deviation from normal operation. This method assumes the worst case scenario where the following have already occurred. The SCADA networks have already been penetrated, and the MTUs have already been compromised. And by the way, MTUs stand for Master Terminal Units, and they monitor, coordinate, optimize, and update the PLCs. And the other assumption is that the PLCs themselves have already been reprogrammed. So with these assumptions, additional steps were added to the TECEP design flow, as shown on the right-hand figure. The new steps are the gray boxes, which primarily focus on source code integration and verification. The system-on-chip platform organization for the solution contains 2 software-implemented blocks and 2 hardware-targeted blocks. The software blocks are the production controller code, which are running on both hard and soft processors, and the hardware blocks are a hardware monitor and a junction box. The platform also presents some isolation. The hardware blocks are invisible to the software blocks, and the software and network access to the programmable logic configuration ports are also disabled. All of these components were implemented on the Zinc 7000 system-on-chip board provided by Xilinx, and we'll be going over these specific platform components over the next few slides. Among the platform components, the production controller sends and receives data through an I/O module, which interacts with the programmable fabric through an AXI bus. Using a real-time kernel, the production controller and I/O module are task managed by the kernel. The production controller itself was implemented as software functions on the ARM Cortex A9 processor on the Zinc 7000 board. The hardware monitor utilizes C code instead of a hardware description language. This makes it easier to integrate a stability-preserving backup controller and the plant system model. The specification guards test if the output of the plant model, physical plant, and prediction unit are in an acceptable range. If they're outside of range, or there's an error status code, The output from the backup controller overrides the production controller's output. The hardware monitor was implemented on the FPGA fabric of the Zinc 7000 board. The prediction unit is comprised of a copy of the production controller and a model of the plant. Controller and plant functions send and receive data across an AXI bus through an I/O module. The production controller I/O module forwards MTU commands to the prediction unit I/O module. The prediction unit was implemented on a microBladesoft processor in the programmable fabric of the Zinc 7000, allowing it to preview attacks that corrupt control algorithm scheduling or driver-level I/O. The prediction unit has 4 modes of operation available. The save mode stores the current state of both the plant and the controller. The restore mode overwrites the current state with the last saved state. Normal mode runs the closed loop system of the plant and controller for 1 cycle. Accelerate mode runs the closed loop for a predefined number of cycles. When the I/O module on the soft processor receives a start signal from the junction box, the closed loop is run in normal mode. The current state is saved, and the closed loop is run in accelerate mode. Once it's completed, the state of the controller and plant before acceleration is restored, and the accelerated plant model's output is passed through the I/O module to the AXI bus. The junction box connects to the production controller, physical plant, prediction unit, and hardware monitor. It manages the system's flow of control and scrutinizes all external transfers to and from the physical plant. The junction box is captured with hardware description language code that mostly defines the connections and is independent of the production and backup controllers, plant model, and operating specifications. So just to summarize the platform components, we have the production controller, hardware monitor / backup controller, prediction unit, and junction box. The production controller is responsible for sending and receiving data and also forwarding master terminal unit commands. The hardware monitor basically just keeps an eye on plant behavior. The prediction unit predicts plant behavior, and the junction box basically acts as a central broker between the production controller, hardware monitor, prediction unit, and the physical plant. So with the solution, formal analysis tools were used to verify functional and security specifications by evaluating mathematical proofs of design code semantic properties. FrameC was used to verify PID code and TECEP additions. FrameC is an open source, modular, static analysis framework for the C language. It enables collaboration between various static analysis techniques implemented as plugins, which can share information. ACSL, which stands for ANSI and ISO-C specification language, was used to capture desired behaviors in other annotations. Annotations can specify preconditions and postconditions of a function, predicates, lemmas, axioms, and other assertions and custom logic functions. ACSL annotations are verified using various plugins within the FrameC framework in order to offer a variety of provers analysis techniques. primacy can be used to verify the values returned by the hardware monitor when a specification guard detects an out of specification condition, and to also validate the behavior of modules called by the hardware monitor. The Jessie plugin was used to make sure the hardware monitor result is driven by the appropriate controller module under all possible conditions. Jessie is a hard logic-based plugin used to prove functional properties via deductive verification. As for hardware synthesis, after formal verification, the hardware monitor's software-defined functions were implemented in the programmable fabric using a C synthesis process. For the junction box, a trivial C function was used to create the AXI interface adapter for the AXI interconnects. So after this solution was designed, it had to be tested in order to validate that it actually worked. So in testing, a simple motor controller example was used to both test and demonstrate the security features described in the proposed solution. The plant in this testing environment was a motor emulated in software functions on ARM. This example was a closed loop system that basically runs millisecond cycles. Latent malicious behavior was inserted into the production controller. So essentially, a logic bomb was inserted into the controller. The malware attempts to increase the plant's output to its maximum value after 350 milliseconds have passed since the plant started running. The malware was tested on the controller with and without the prediction security mechanism of the proposed solution, and comparisons were also made between the tests on the controller with and without overall protection. So here's a graph displaying the results of the tests with absolutely no protections enabled. The blue line shows the plant's output without the protection of the new solution. So we can see that when the malware takes effect at 350 milliseconds, the plant starts to approach its safe output limit of 3.2, and then it suddenly just starts exceeding that 3.2 level. And it also just doesn't return back to normal baselines. And then here's a graph that compares the results of the plant output when protections are enabled, this time with and without the prediction mechanism. So with the prediction mechanism, we're also looking at the prediction mechanism combined with the hardware monitor. And without the prediction mechanism, we're only looking at only the hardware monitor being enabled. The brown dotted line in this graph shows the plant behavior when only the hardware monitor feature is enabled. So we can see that the plant approaches its safe limit of 3.2 before the backup controller kicks in. So basically the backup controller brings the plant output back down to stable levels. The blue line, on the other hand, shows the plant behavior when both the hardware monitor and prediction features are enabled. So with prediction, the hardware monitor proactively invokes the backup controller before the malware even takes effect, thus preventing the plant from reaching an unsafe state. This is because the prediction unit forecasts the future consequences of the malware. So even though the proposed solution was proven to have worked, there are still limitations and trade-offs associated with it. So with the TECEP additions, the system-on-chip solution provides a lower cost, on-chip, digital logic alternative to classical mechanical interlocks of safety-critical environments. However, the preview window of attack from the prediction unit is limited by the processing power and the need to synchronize the model with the physical plant to keep up with changes due to disturbances, noise, or commands. There's also a higher maintenance cost because there's no ability to remotely update the TECP logic, so there must be PLC access to modify the model, process specifications, and backup controller. So just as a recap, current approaches to industrial control system security apply only generic protections at the hardware or software layers to help isolate and secure applications. The solution proposed in this paper used application-specific hardware to mitigate specifically software reconfiguration attacks. In terms of real-world applications, TECEP is currently being applied to an electromechanical physical plant, basically in order to test the solution in an increasingly complex system. TECEP's scalability within cyber-physical systems and applicability to non-control domains are also currently being investigated for future work.